Well, let us describe the properties of the obtained metric. So the metric that we have obtained has the following form, where R is implicit function of U and V. To remind you, du dv is equal to minus r squared d omega squared. And I remind you that u and v are related to original Schwarzschild coordinates as follows: 2rg minus 2rg exponent of minus t minus r divided by 2rg times r divided by rg minus 1/2, and v is equal to 2rg exponent of t plus r divided by 2rg multiplied by r divided by rg minus 1/2. So, and now we're going to draw and describe this space-time. Before doing that, let me remind that if we multiply u by v, we obtain that r divided by rg minus 1 exponent of r divided by rg is minus uv divided by 2rg squared. And if we divide v by u, v divided by u is exponent of t divided by rg. So now one can see that for constant r we have hyperbolas. For constant t we have straight lines which are passing through the origin. So straight, this is a constant, so we get the straight line. And the hyperbolas degenerate to the, when r goes to rg, the hyperbolas degenerate to the lines defined by this equation. So to the lines u equals to 0, v equals to 0. So we want to draw the lines. But to do that, let me stress that u and v are light-like coordinates. So the equation du equals to 0 and dv equals to 0 defines light rays for light ray propagation for constant angles. So it is convenient to define this new t minus r and v equals to t plus r coordinates. And in this new coordinates, t and r, so let me draw them. So this is t, this is r. Now one can see that the line v is this one. So this is line v. This is the line u. This is the line u. And one can see that constant r corresponds to hyperbolas. Constant r corresponds to hyperbolas, like this. So the situation is very similar to the one which we have encountered in Rindler space, as you remind, as you remember in the first lecture. So this is r constant. And constant t are straight lines passing through the origin. So this is t constant. T constant. So again, this line corresponds, as one can see from this formula. This corresponds to r equals to rg. This is u0, u0. And this also corresponds to r equals to rg. And simultaneously, this corresponds to t equals plus infinity, as can be seen from here. And this corresponds to t equals to minus infinity, also, as can be seen from here. So this is u equals to 0, this line. And this is v equals to 0, this line. And Schwarzschild coordinates cover only this quadrant, while these u and v are similar to Minkowski coordinates covering the whole space. So Schwarzschild coordinates, original t and r coordinates, are similar to Rindlerian coordinates, rho and tau. Remember that we have encountered in the first lecture. But what is important here, that using these coordinates, one can continue to r less than rg, perhaps using, well, anyway, one can continue beyond this point, but this metric is singular, as we discussed during this lecture, along the hyperbola, which corresponds to r equals to 0. This hyperbola has two images, here and here. So this is Kruskal-Zekeres coordinates and their properties, and we are now ready to draw Penrose-Carter diagram for this case. So we have obtained Kruskal-Zekeres coordinates, which is t big, well, it's more appropriate to use x letter than r here, because x is ranging from minus infinity to plus infinity, while I assume that r is ranging from 0 to infinity. So x, so, and this is then an v coordinate. This is an u, light-like u coordinate. And this Kruskal-Zekeres spacetime is not valid beyond this point, so it's not valid here. So this is r equals to 0, this hyperbola. So it's not valid beyond this point. So the situation is more or less, up to this, the situation is more or less similar to Rindler, a relation between Rindler and flat spacetime. We can transform from u, which is t minus x, and v, which is t plus x, to the, which we can do the same transformation, basically, as we did for Minkowski space, to the new coordinates psi and psi, from this two coordinates to this, the same transformation. Because as you may notice, so we just we are concerned about this part only, the relevant two-dimensional part of this metric. The relevant part is just, the relevant two-dimensional part is just this guy, rg dv du. So we concentrate on this and make in this space, non-compact space, this here, make in this space the same transformation as before. So then the diagram, Penrose-Carter diagram, in this case, is basically the same square as before, with one important difference. So what we have is that, so we basically should obtain the square, the same square as before, here psi, psi, but with important difference because of this. We have to chop off here the upper and lower triangular part, chopping off this. So this is r equals to 0, r equals to 0, where it is mapped. So, but it is important that under the conformal map, under the standard conformal map, this curves would map to something which is curvy here, but by adjusting conformal factor, one can make them straight. And now, so this is a Penrose-Carter diagram for the Schwarzschild spacetime. Let me discuss it in a greater detail.